reservations in two-way slabs by means of yield lines. This video will deal with the cases 31 to 35, and it's about a concrete slab simply supported on two opposite sides and fixed in support on the two other sides. This will handle case 34, which is a centric hole by means of attracting yield lines. We have a rectangular slab and there is a centric reservation in it. It's centric in both directions. And the dimensions are D1 and D2, D1 in the vertical direction, D2 horizontal. And it's situated central, so it means that on the left-hand side there is D4, and on top and bottom there is D3 as a distance. The method of yield lines, we are using the fact that the whole reservation is attracting the yield line, so it means from the corner of the reservation to the point of intersection of two axes of rotation. So this yield line is independent of the angle here. So we do not use the 30, 45, 60 rule. We've seen that this is a more realistic yield line when you approach when you have large reservations, it is a more realistic yield line. So in the four corners, we will have those yield lines, independent of the angle, independent of if this is now fixed end and this is, for instance, simply supported. It does not matter. It goes from the intersection to the corner of the reservation. Of course, we have also the yield lines of the negative bending moments on the two fixed ends. What are the conditions? Two-way slab B is between A and 2A. The maximum size of the reservation, of course, is that D2 must be smaller than B and D1 is smaller than A. And the horizontal symmetry means that B is equal to D4 plus D4 plus D2. A is equal to D1 plus D3 plus D3. The value of D3 and D4 should be taken large enough. If the value, for instance, of D3 is getting very small, then you have a non-realistic yield line. Then it's not very wise to do so. So we recommend that for D3 and D4 you should take a minimum of, for instance, 0.2 times the smallest size of the slab. So this is D4 is, for instance, 20% of A. These are the conditions. Now we can have some reservations fulfilling all those conditions. You will have, of course, the centric reservation, rectangular or square or horizontal or vertical. We can calculate now the work done by the external forces. It is equal to, when we are look at the triangle shaped surfaces in the green location, then we see that when we got D4 times D3 for this total, it comprises of triangles, so the mean deflection is delta over 3. And we got that 1, 2, 3, 4 times, which is this amount. Then we go to the rectangular sections. Then we have the surface is D3 times D2. We got that 2 times. And D4 times D1. We also got that 2 times, which is that. And the mean deflection is delta over 2. We use dimensionless parameters. So alpha 1 is equal to D1 divided by A. Alpha 2 is D2 divided by A, and so on. And alpha is B over A. Of course, because it's centric, D4 is a function of B and D2, and D3 is a function of A and D1. Then we can substitute those values in this formula, and we arrive at this expression. So E is a function of alpha, alpha 1, and alpha 2. The work done by the internal forces is then equal to the yield line projected on this axis So it is the length is d4, and the rotation is of course delta divided by d3. So we have d4 divided by d3, and on the other side, when you have this as rotation axis and you project this yield line on this axis, then you got d4 divided by, then you got d3 divided by d4. That's for one corner, and all corners are the same. So we have 4 times this situation. What's left are the negative bending moments of the negative yield lines. So it's alpha divided by d4, and we got that 2 times. Substituting the values, we arrive at this expression. And by making d equal to E, we get the maximum bending moment M, and it's given by this expression. The bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. And for the horizontal case, when alpha is bigger than the square root of 3, we know that the bending moment without the reservation is equal to this expression. See the previous videos in the same playlist. And for the vertical yield line pattern, when alpha is smaller than 1.7, then the bending moment without the reservation is equal to this. So M0 is equal to this function. And the bearing capacity is, of course, a function of alpha, alpha 1, and alpha 2, and is given by this. For instance, for a case like that, alpha is 1.5, so this 1.5 times this. Alpha 1, which is the vertical, or is half of this side, so alpha 1 is 0.5, and alpha 2 is 1/10 of this side is 0.1. And only with those 3 parameters the situation is defined, and you can calculate directly what is the bearing capacity, and it's 152. So it means by making a reservation like that in the slab, you do not touch the bearing capacity. You in fact increase the bearing capacity of the slab. We can now make a graph of x-axis is alpha, it's B over A, and the y-axis is the bearing capacity. Why? Because it's a mean of studying this type of centric reservation. What is this type of reservation doing with the bearing capacity on the slab? And we are interested in those reservations that are lowering the bearing capacity. We can now make different graphs. This one is made in function of alpha and with B1 equals to 0.1, which is a very narrow reservation. And the length of the reservation is going from 0.1 to 0.8. So alpha 2 is from 0.1 to 0.8, and alpha 1 is 0.01. Then you can draw different curves following D2, and you see the area where you have to be very careful. You can immediately see this. We can give an example. Suppose that you have a slab with the ratio B over A equals to 1.8. Then you see on this point that for centric hole of 0.1 times A as diameter, you lose some bearing capacity. Not much, but you lose some bearing capacity. You lose 3%. The next, for instance, for alpha equals to 0.1 and alpha 2.2, which is a reservation like this, you lose more bearing capacity, 6%. And then you increase the reservation, you lose 10% of the bearing capacity. And when you make the reservation equal to 0.8 times the smaller dimension, so you got this picture, you lose something like 13%. So this is a way of that you can study the location of the reservation that you want in the slab and the effect on the bearing capacity. And of course, the last one, this is with 0.8, sorry, the other was with 0.6, you have 87.7. Now, it's the same type of graph, but this time we take alpha 2 as the variable. Alpha 1, we keep it on 0.1. See the previous example, and this alpha 2 is changing. And now the alpha, we have different curves for different alphas. Now you will see this is the area that you are interested in. So we'll blow it up a little bit. So it's the same graph, but we only go to 110%. So it's this portion, it's that portion. Now we know that every combination below the line of 100 we want to avoid. So this area we want to avoid. So now you can properly choose the dimension, or you can easily see what is the effect of the reservation in the slab. We can have a square hole in a square slab. And then we have this situation. And for instance, in this case, D1 is equal to D2, and alpha 1 is 0.6. So when you make alpha 1 larger than 0.6, you do not have realistic yield lines at the end. So there's also a yield line here. And when this reservation is coming very close to this yield line, then you have almost two yield lines, one in the neighborhood of the other, which is not realistic. This will not happen. So we assume that alpha 1 is smaller than 0.6, something like that. Then we know that the bending moment is then a function only of alpha 1, because the other parameters are known. And with the previous formula, we find that m in function of alpha 1 is equal to this, because alpha is here 1. That's a square slab. Then it's only a function of alpha 1. The bearing capacity is the same. We fill in the bearing capacity. The alpha 1 equals to alpha 2, and alpha is equal to 1. Then we got this expression. And the bending moment without the reservation is then equal to this expression. So you can put it into a graph. Vertical axis, the bearing capacity. Horizontal is the size of the reservation. And now we can clearly see. But first of all, what we notice is that here in this element, when alpha 1 is 0, so when there is no reservation, the bearing capacity is not 100%. So something is wrong, because it should be M0. Now, bear in mind that this formula is calculated with the 30, 45, 60 rule for the yield lines. So this M0 is calculated with a yield line with an angle here of 60 degrees and there 30 degrees. And the formula that we got here, this calculated with the tracking yield lines directly. So that's why there is a difference for alpha 1 equals 0, because it's the difference, in fact, between the choice of tracking yield lines and the choice of 30, 45, 60 rule. The other point that you are interested in is this, where the bearing capacity is 100%. So every reservation bigger than 0.3 times smaller size leads to no loss of bearing capacity. And every reservation smaller than 0.3 leads to bearing capacity. So this is a little bit counterintuitive, that the smaller the size of the reservation, the bigger the effect on the bearing capacity. And the maximum bearing loss of bearing capacity is 7% and occurs at alpha 1 equals to 0.13. So we remember that the bearing capacity is lower than 100% when alpha 1 is between 0 and 0.3. Shortly, we can say avoid making holes smaller than 1/3 of the slab dimension, square slabs.